Quick question. When was the last time every major space agency on Earth simultaneously went quiet about the same cosmic event? I'll wait. The answer is never. Not like this. Oumuamua in 2017 generated a flood of data, papers, press releases. 2I-Borisov in 2019. Same thing. But 3I-ATLAS, our third confirmed interstellar visitor, we've got fragments, whispers, and an awful lot of very careful non-statements. Now, maybe that's just cosmic bad luck, timing issues, boring explanations, or maybe, just maybe, silence is the only rational response when you've seen something you're not ready to announce. Stay until the end, because we're going to calculate exactly how many days of continued silence it takes before we're forced to conclude the obvious. If this mystery has you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about 3I-ATLAS. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. Thank you for having our back. Part 1. The Void Speaks Louder. Picture this. A single fuzzy dot on a screen. That's all we have. The European Space Agency managed to capture it during a Mars flyby, a faint smudge against the cosmic backdrop, barely distinguishable from the noise of space itself. This is 3I-ATLAS, the third known interstellar visitor to our solar system, photographed at a distance of roughly 29 million kilometres from the red planet. It's not much to look at, honestly. A blur, a whisper of light. But here's what makes your skin prickle. That blur is all we've been given in 96 hours, maybe longer, of near total silence from the world's most powerful space agencies. Think about how fast information usually moves in our hyper-connected world. When an asteroid makes a close pass by Earth, we get press releases within hours. When a supernova flares in a distant galaxy, astronomers are tweeting about it before the light finishes its journey through our atmosphere. The machine of modern space science runs on immediacy, on sharing, on the thrill of discovery broadcast to anyone with an internet connection. So why, when an object from another star system passes through our neighbourhood, do we get nothing? NASA has been remarkably quiet beyond their earlier announcements. China's space program? Silent. The United Arab Emirates, with their Hope orbiter at Mars? Not a word about attempting observations. It's as if someone pressed a cosmic mute button right when we should be hearing the most noise. You might be thinking this is just bureaucratic delay. Agencies need time to verify data, to run calculations, to make sure they're not about to embarrass themselves with a false claim. That's reasonable. That's how science works. But here's the thing. We've had interstellar visitors before. When Oumuamua tumbled through in 2017, the scientific community erupted with activity. Papers flew out, data got shared, telescopes around the world scrambled to catch one more glimpse before it vanished into the dark. When 2I-Borisov showed up in 2019, we had spectrum analysis, composition estimates, and orbital predictions splashed across news sites within days. The machine worked the way it was supposed to work. This time feels different. This time, the silence itself has become a character in our story, a presence as tangible as the object we're trying to understand. When absence becomes the loudest signal in the room, you have to ask yourself what that absence is trying to tell you. Is it caution? Is it confusion? Or is it something else entirely? Something that makes agencies choose their words so carefully that they'd rather say nothing at all. Let me ground you in something important. 3I-ATLAS is not our first interstellar visitor, but it might be the most significant. The stakes have changed since Oumuamua. Back then, we were children seeing something magical for the first time, scrambling to understand what it meant. Now we're older, maybe warier. We've had time to think about what it means when objects from other star systems can reach us, what possibilities that opens up, what questions it forces us to confront. And maybe that's why the silence feels heavier this time. Maybe we're not sure we want to know the answers. In just a moment, we're going to interrogate that European Space Agency image, pixel by pixel, and discover why it shouldn't even exist under normal expectations. We're going to ask why spacecraft designed to study Mars would bother turning their instruments toward a faint object millions of kilometers away. But before we get there, I want you to sit with this discomfort. If silence persists, if no new data emerges, if the agencies continue to offer nothing but recycled statements and old observations, we inch toward the worst-case hypothesis by default. Not because we want to, not because it's the most likely explanation, but because human minds abhor a vacuum, and we will fill silence with speculation whether we mean to or not. There's a pattern in the history of space science. Sometimes delay creates rumour. Back in 2011, when Comet Elenin was approaching, there was a lag between observation and official statement. In that gap, the internet spun wild theories. It was going to cause earthquakes, it was being followed by a spacecraft, it was going to somehow pull Earth out of orbit. None of it was true, of course. The comet broke apart before it even reached perihelion. But the silence beforehand, that temporary void of information, allowed speculation to flourish like bacteria in a warm dish. The lesson? When scientists don't speak, someone else will speak for them. So before we assume conspiracy, before we let our imaginations run completely wild, we need to inspect the evidence we do have. We need to look at that fuzzy dot and understand what it can and cannot tell us. Because if we're going to talk about silence, we need to first understand what was spoken, however faintly, in that single captured image. Part 2. The ESA image that shouldn't exist. Let's talk about the European Space Agency's Mars orbiters. ExoMars Trace Gas Orbiter and Mars Express are not designed to be cosmic paparazzi. These spacecraft exist for one purpose: studying Mars. The Trace Gas Orbiter sniffs the Martian atmosphere, searching for methane and other gases that might hint at geological or biological activity below the surface. Mars Express maps the planet's surface, tracks its weather, probes beneath its soil with ground-penetrating radar. These are specialised instruments built for a specialised job, like sending a portrait photographer to document geology. They're good at what they do, but what they do is very specific. So when the ESA announced they captured an image of 3I-ATLAS during its closest approach to Mars on October 3rd, 2025, at a distance of approximately 29 million kilometres, the first question should be, how? These spacecraft weren't designed to track extremely faint objects moving through deep space. Their cameras are optimised for planetary observation, for capturing the rusty surface of Mars in crisp detail, not for teasing out the feeble photons bouncing off a distant visitor. It's like using a microscope to look at the moon. Sure, you might see something, but it's not what the tool was built for. What they captured was, to be generous, underwhelming. A faint fuzzy blob. No clear coma. The glowing cloud of gas and dust that typically surrounds a comet's nucleus. No resolved tail stretching away from the sun. No distinct nucleus, that solid core of ice and rock we'd expect to see. Just fuzz, just noise made barely visible. Scientists, even the skeptical ones, described the observation as challenging, as barely detectable. One researcher called it at the limits of what these instruments can resolve. Another said it was consistent with a very faint coma, but with significant uncertainty. For a comet, which is what 3I-ATLAS is supposed to be, we expect certain things. Comets are dirty snowballs, frozen remnants from the formation of solar systems. As they approach a star, the ice sublimates, turns from solid to gas without passing through liquid, creating that characteristic coma and tail. We should see jets of dust, asymmetric features, maybe even discrete structures where vents on the nucleus spew material into space. We've seen this countless times with comets in our own solar system. It's predictable. It's understood. So why does 3I-ATLAS look like someone smudged a charcoal pencil across the sensor? The verified explanations are straightforward. It's extremely dim. It's extremely far away. The exposure time might have been insufficient. Motion blur is a real concern when you're trying to photograph something moving at tens of thousands of kilometers per hour. Stacking multiple images to increase signal-to-noise ratio can introduce artifacts, create false features, or smooth out real ones. All of this is plausible. All of this fits within the boundaries of normal observational astronomy. We're pushing these instruments to their absolute limits, and sometimes at the limits you don't get clean data. You get ambiguity. But let's walk to the edge of that ambiguity and peer over. What if the fuzz isn't a limitation of our instruments? What if it's a feature, not a bug? Think about signal disguised as noise. If you wanted to hide something in plain sight, making it look unremarkable is pretty effective. A distinct shape, a geometric pattern, obvious structure that would attract attention. But a fuzzy blob? That's dismissible. That's exactly what you'd expect from a dim, distant comet that's barely detectable. It blends into our expectations so perfectly that we might not think to question it. I'm not saying 3I-ATLAS is deliberately hiding. I'm saying the data is ambiguous enough that it could hide something and we wouldn't know. Maybe there are structural features within that fuzz that we can't resolve with current imaging. Maybe the fuzz itself is engineered, a cloud of reflective particles surrounding something we're not meant to see yet. Or maybe it's exactly what it looks like. A comet so far away and so faint that we're lucky to see anything at all. The problem is, with this image alone, we can't tell the difference. Scientists hate ambiguity. They want clean data, clear signals, results that point in one direction with confidence. When data sits in that murky middle ground, when it could support multiple interpretations, the instinct is to wait. Gather more observations, run more models, check and double-check before making claims. And maybe that's part of the silence. Maybe NASA, maybe other agencies, they're sitting on data that's just as ambiguous as this ESA image, and they're trying to figure out what it means before they say anything publicly. Because once you say something, once you put an interpretation out into the world, you can't unsay it. You can't take it back. But here's what bothers me. Even ambiguous data usually generates conversation. Scientists argue about interpretations. They publish competing papers. They debate in conference halls and on Twitter. The process is messy, but it's visible. With 3I-ATLAS, even that messy process seems muted. It's not that no one's talking. It's that the volume is turned way down, like everyone's speaking in whispers, afraid of being overheard. In our next part, we're going to peer into what NASA could have had but hasn't said, or might be holding back. We're going to look at the data they've released, the data they've hinted at, and the conspicuous gaps in between. Because if this ESA image is ambiguous, what NASA might have could be far more revealing. The question is whether they're choosing to reveal it. Part 3. NASA's quiet corridors. NASA has not been completely silent. Let's be fair about that. They've released materials. There's a discovery animation on their Comet 3I-ATLAS multimedia page, showing the object's trajectory through the solar system, its hyperbolic orbit making clear it's not gravitationally bound to our Sun. There's Hubble imaging from July 21st, 2025, showing what they described as a dust cocoon shape, a roughly spherical cloud of particles surrounding the nucleus. They've issued statements assuring us there's no threat to Earth, that the orbit has been calculated precisely, that 3I-ATLAS will pass through and leave without incident. They've even responded to alien speculation, with a spokesperson saying something along the lines of "We follow the evidence, and currently the evidence is consistent with a natural object." All of this is standard procedure. This is what space agencies do. They inform the public, they provide reassurance, they present data in digestible formats. But here's where it gets interesting. Look at the timeline. The Hubble observations were made on July 21st. They were released. When? Check the dates on the press releases. Calculate how many days passed between observation and publication. Now compare that to typical Hubble release schedules. Factor in the extraordinary nature of this object, the third confirmed interstellar visitor ever detected. Does the timeline make sense? Or does it feel stretched, like someone took the normal process and added a buffer zone, a pause, a moment to think before speaking? Then there's the Perseverance incident. On October 4th, 2025, Avi Loeb, the Harvard astronomer who's become something of a celebrity for his willingness to consider exotic hypotheses, posted analysis of what he claimed was a Perseverance navcam image showing a stripe. A long elongated feature captured by the rover's navigation camera, which Loeb interpreted as possibly being 3I-ATLAS. The geometry was challenging. The rover is on Mars. 3I-ATLAS was tens of millions of kilometers away at that point, and capturing a faint object through Mars's dusty atmosphere with a camera designed for navigation seems unlikely at best. Skeptics immediately pushed back. Stacking multiple frames to increase signal can produce elongated artifacts, especially if there's any camera motion, or if the object is moving relative to the frame. Exposure time matters. Too short, and you don't gather enough photons. Too long, and motion blur turns a point source into a streak. The constraints don't line up nicely. Either the exposure was too short to detect something that faint, or it was long enough that the object should have appeared as a streak, not a stripe with somewhat defined edges. The debate became technical quickly, diving into signal processing, photon counting, and the specific capabilities of the NavCam sensors. NASA never officially confirmed or denied Loeb's interpretation. They didn't release the raw data for independent analysis. They didn't issue a statement saying, "We looked at it, here's what we think." They just didn't engage. And that's odd. When a prominent scientist makes a claim about NASA data, even a controversial claim, the agency usually responds. They might say, "We're looking into it," or "Our analysis differs," or even, "We don't have enough information to comment." Silence is not the typical response. So let's reason through what might be happening inside NASA's corridors. Maybe they're verifying the data against multiple sources. Space science is rigorous, and no one wants to announce something significant only to retract it later, when better analysis comes through. Maybe there are internal disagreements about how strongly to present any speculative interpretations. Bureaucracies are not monolithic. Different scientists, different departments, different administrators all have opinions, and reaching consensus can take time. Maybe data is being intentionally bottled until they achieve that consensus, until everyone agrees on what can and cannot be said publicly. Or maybe, and this is where we wade into deeper water, something was seen that's inconvenient or sensational, and they're waiting on corroboration before speaking. Think about the implications of announcing something truly anomalous. If NASA came out and said, "We've detected features inconsistent with natural cometary behaviour," the reaction would be immediate and intense. Media would explode. Social media would catch fire. Every conspiracy theorist would claim vindication. And if it turned out to be wrong, if further analysis showed it was just an artifact or a misinterpretation, the damage to NASA's credibility would be significant. The incentive structure pushes toward caution, toward waiting until you're absolutely certain before making bold claims. But caution can look a lot like concealment, especially when the public is hungry for information. The line between responsible science and strategic silence is thin, and from the outside, we can't always tell which side of that line we're on. What we can observe is that NASA's communication pattern feels different this time, more measured, more sparse, more carefully controlled. Whether that's due to scientific uncertainty or something else, we simply don't know, and that uncertainty is going to deepen as we expand our view. Because NASA is not the only player in this cosmic drama. In our next part, we're going to pull back the curtain globally and see how silence is not just NASA's domain. It's a pattern that stretches across national borders, across space agencies, across the entire apparatus of modern astronomy. And when silence becomes a pattern, when it spans continents and institutions, you have to ask whether it's coordinated, whether there's something everyone knows but no one wants to say. Part 4. The global curtain. Space is not an American monopoly. Let's establish that up front. The cosmos belongs to everyone, and multiple nations have the capability to observe, track and study objects like 3I-ATLAS. China's National Space Administration operates a sophisticated array of ground-based telescopes and space assets. The United Arab Emirates has HOPE, their Mars orbiter that's been sending back stunning data about the Martian atmosphere since its arrival in 2021. The European Space Agency, beyond their Mars orbiters, has access to ground-based facilities across the continent. Russia's Roscosmos, despite being diminished from its Soviet-era prominence, still maintains observational capabilities. India's ISRO has been making strides in deep space observation. This is a global enterprise, and when something as significant as an interstellar visitor passes through, you'd expect global participation. What we're seeing instead is a chorus of silence. China has not issued any press releases about observations of 3I-ATLAS. The UAE has not announced attempts to reorient HOPE's instruments toward the object. ESA released that one fuzzy image we discussed, then went quiet. Roscosmos has been focused on their struggling space station ambitions. ISRO has not publicly commented. It's as if everyone simultaneously decided this wasn't worth talking about, which makes no sense given the scientific value of studying an interstellar object. Let's explore possible reasons for this collective quiet. First, technical limitations. Not every spacecraft or telescope is positioned or equipped to observe a faint, fast-moving object millions of kilometres away. The UAE's HOPE orbiter is optimised for atmospheric studies of Mars, not deep space object tracking. China's space telescopes might not have had a clear line of sight during the critical observation windows. Roscosmos might simply lack the resources or functional assets to contribute meaningfully. These are all legitimate technical constraints. Second, internal policy restrictions or non-disclosure norms. Some nations treat space program activities with significant secrecy. China, for instance, is not known for rapidly releasing scientific data to the global community. Information flows through official channels on official timelines, and those timelines are not dictated by scientific curiosity alone. If China's telescopes observed something interesting, we might not hear about it for months or years, if at all. This is simply how their system operates. Third, and this is where we enter more speculative territory, coordinated silence. An embargo across agencies, whether formal or informal, where everyone agrees to hold back until certain conditions are met. Maybe until data reaches a threshold of certainty. Maybe until a lead agency, like NASA, gives the go-ahead. Maybe until diplomatic or security considerations are addressed. Space agencies do coordinate, especially on major projects or discoveries. They share data through agreements that sometimes include provisions about public release timing. The precedent is confusing, though. When Oumuamua blazed through our solar system in 2017, we saw active international cooperation. Data flowed between agencies. Papers were published rapidly. Different telescopes, different nations, all contributed pieces to the puzzle. When 2I Borisov arrived in 2019, the pattern repeated. Information sharing happened quickly. Press releases coordinated but did not delay each other. The scientific community operated in the open, the way science is supposed to operate. With 3I-ATLAS, that openness has contracted. There's less coordination visible from the outside, fewer cross-announcements, fewer instances of agencies citing each other's observations. It feels more siloed, more insular. Each agency seems to be operating in its own bubble, and the bubbles aren't connecting the way they did before. Whether that's intentional or just an artifact of timing and circumstance, it creates an impression of fragmentation, of a system that's not functioning quite the way it used to. Some media outlets have noted these gaps. Articles have appeared asking why China hasn't announced plans to study 3I-ATLAS with their extensive telescope network. Others have questioned why the UAE, with a perfectly positioned orbiter at Mars, hasn't attempted any observations. The questions are valid, but the answers are not forthcoming. Official channels remain largely silent on these points. Here's a speculative scenario. Maybe there's an implicit understanding, as don't talk until NASA does signal, running through the international space community. NASA remains the most prominent space agency globally, with the largest budget, the most assets, and arguably the most credibility. If NASA is being cautious about how they frame observations of 3I-ATLAS, other agencies might follow that lead. Not because they're taking orders, but because they're reading the room. They're seeing NASA's measured approach and thinking, maybe we should be careful too. Maybe we should wait and see how this plays out before we stick our necks out. But that creates a feedback loop. If everyone is waiting for someone else to speak first, no one speaks. If everyone is being cautious because everyone else is being cautious, the caution becomes self-reinforcing. The silence perpetuates itself, not because of any conspiracy or coordinated suppression, but because of a collective choice to avoid being the first to make a bold claim. It's like a group of people standing at the edge of a cold pool, each waiting for someone else to jump in first. Is cosmic secrecy becoming a new norm? Are we entering an era where space agencies default to silence rather than transparency, where the impulse to control the narrative outweighs the tradition of open scientific inquiry? Or is this just a temporary aberration, a quirk of this particular observation, and normal patterns will resume once the data is clearer? We don't have answers yet. What we have are questions, and those questions multiply the longer the silence persists. If this silence continues, if no new data emerges from any agency anywhere in the world, the worst-case framing begins to loom larger. Not because it's likely, but because human psychology fills voids with fears. In our next part, we're going to confront that worst-case scenario head-on, not to endorse it, but to understand why it becomes psychologically, if not scientifically, inevitable when information disappears behind institutional walls. Part 5. The worst-case scenario frame. Let's say it plainly. If this silence continues, if agencies keep holding back or saying nothing of substance, the alien hypothesis becomes psychologically inevitable, not scientifically proven, not even scientifically likely, but Inevitable in the sense that human minds will drift there, will construct that narrative because it's the narrative that makes the silence make sense. We're storytelling creatures. When we don't have data, we create stories. And the story of extraterrestrial visitation is one of the most powerful stories our species has ever told itself. So let's sketch out what a worst-case scenario might look like. Not as prediction, but as thought experiment. Imagine 3I-ATLAS is not a comet. Imagine it's an artifact, something built by intelligence, sent into the cosmos for purposes we don't yet understand. Imagine that agencies detected features, signatures, behaviours that don't align with natural explanations. Maybe there were spectroscopic anomalies, emission lines that don't match any known comet composition. Maybe there were subtle course corrections, tiny adjustments to trajectory that can't be explained by outgassing or gravitational interactions. Maybe during its passage behind the Sun, during the period of occultation when we couldn't observe it directly, something happened that changed its velocity, or heading in ways that violate what comets should do. Now imagine this object is on some kind of trajectory that intersects with Earth or its orbital path. Not immediately, not in a threatening way, but in a way that suggests intention, targeting, purpose. The worst-case scenario is not just that it exists, but that it's coming here, or sending information here, or preparing something here. That would be the kind of discovery that shatters frameworks. Every assumption about our place in the universe would be up for revision. Every question about whether we're alone would have an answer, and that answer would be terrifying, not because aliens are necessarily hostile, but because the uncertainty would be unbearable. Let's place this in historical context. The scientific community has dealt with false alarms before. The WOW signal in 1977, that powerful narrowband radio signal detected by the Big Ear telescope, looked for a moment like it might be extraterrestrial communication. It was never detected again, never explained satisfactorily. It remains an anomaly, but not proof of anything. Comet Elenin in 2011 became the subject of wild speculation, people claiming it would cause earthquakes or pole shifts or some other catastrophe. It broke apart before perihelion. It was nothing. Hysteria evaporated. The UFO/UAP disclosure process, which has been unfolding in stages over recent years, offers another model. Governments have started releasing previously classified footage of aerial phenomena that can't be easily explained. They're doing it gradually, controlled drip of information, letting the public acclimate to the idea that there are things in our skies we don't understand before moving to any bigger revelations. It's a careful choreography, designed to avoid panic while acknowledging uncomfortable truths. If 3I-ATLAS is something anomalous, a similar model might be in play. Agencies might be preparing the ground, waiting for the right moment, trying to figure out how to say something without causing mass hysteria or undermining their own credibility. Because here's the thing, if you announce, "We've detected an artificial interstellar object," you can't walk that back. You can't say, "Oops, our mistake," after the entire world has processed that information. The stakes are too high to get it wrong, so the incentive is to be absolutely certain before saying anything. But from the outside, caution and concealment look the same. The public can't tell the difference between "we're being careful" and "we're hiding something." And the longer the silence lasts, the more the second interpretation gains traction. Conspiracy theories don't emerge from nothing. They emerge from the gaps between what people think they should know and what they're being told. When those gaps widen, when the silence stretches, when agencies offer reassurance without offering data, the conspiracy theories write themselves. I want to be clear. This worst-case scenario is speculative. It's not the baseline hypothesis. It's not what the data currently supports. But it is a logical endpoint given the current conditions, a place where minds will wander if the silence persists and deepens. An understanding that psychological trajectory is important, because it shapes how we interpret everything that comes next. If people are primed to expect the worst, they'll read ambiguity as confirmation. They'll see normal bureaucratic delay as evidence of cover-up. The perception becomes its own reality. So we acknowledge this possibility as one branch of inquiry. We keep it on the table, not as a closed claim, but as an open question. Because dismissing it outright, refusing to even consider it, doesn't make it go away. It just pushes it underground, where it ferments into something less rational, less tethered to evidence. Better to bring it into the light, examine it, and understand why it holds psychological power even if it lacks scientific proof. Now we descend into the details, into the data buried in noise, into anomalies that might be signal or might be static. In the next part, we'll look at what amateur astronomers and professional observatories have been quietly reporting, the orbital residuals, the spectroscopic hints, the whispers that circulate beneath the official silence. Because if silence is the public face, noise is the private undercurrent, and in that noise there might be something worth hearing. Part 6. Data buried in the noise. Astronomy has always been a conversation between signal and noise. Every photon that reaches our telescopes carries information, but so do the gaps between photons, the moments of darkness, the statistical fluctuations that blur the line between detection and imagination. When we look at 3I-ATLAS, we're not just looking at an object, we're looking at data streams, orbital fits, spectroscopic signatures, residuals in tracking calculations, and in those residuals, those tiny deviations from predicted paths, some people are seeing patterns. The Minor Planet Center maintains logs of small body tracking data. Amateur astronomers and professionals alike contribute observations, feeding into models that calculate orbits with increasing precision. For most objects, the fits are clean. Observations match predictions within acceptable error margins. But with 3I-ATLAS, some trackers have noted odd residuals, small non-gravitational accelerations that don't quite fit the standard comet outgassing model. These could be measurement errors, they could be artifacts of combining data from different observers with different equipment, or they could be real deviations that suggest something about the object's behaviour doesn't match our expectations. Non-gravitational forces are common with comets. As ice sublimates on the sunward side, it creates thrust, like a tiny rocket engine. This causes comets to accelerate or decelerate in ways that pure gravitational calculations don't predict. Astronomers have models for this. They account for it when refining orbits. The problem is, the magnitude and direction of these forces should correlate with the comet's distance from the Sun, its rotation rate, the distribution of volatile ices on its surface. If those correlations don't hold, if the forces are too strong or too weak or pointing in unexpected directions, it raises questions. Some online forums, the places where amateur astronomers gather to share observations and argue about data reduction techniques, have been buzzing with claims about 3I-ATLAS showing unusual accelerations. One poster claimed the object exhibited a delta V inconsistent with water ice sublimation alone. Another suggested the trajectory showed periodic corrections, as if something were adjusting the course at regular intervals. These claims are unverified. They're based on publicly available tracking data that anyone can download and analyse, but different analysts get different results depending on how they process the numbers. Noise and signal blur together at these precision levels. Then there's the spectroscopy. The James Webb Space Telescope, humanity's most powerful infrared observatory, turned its gaze toward 3I-ATLAS during its approach. Reports emerged, not from NASA directly, but from secondary sources citing unnamed researchers, claiming Webb detected an unusually high carbon dioxide to water ratio, something like 8:1, far higher than typical comets. Carbon dioxide is not uncommon in comets, but ratios that skewed suggest unusual composition, maybe formation in a different environment, maybe a different kind of ice mixture than what we see in our solar system's comets. Other spectroscopic hints have circulated, unexpected emission lines perhaps, from organic compounds that don't match standard comet chemistry. Or maybe those lines are just noise, artifacts of atmospheric correction, quirks of how the telescope's instruments responded to a faint moving target. Disputes rage in the literature and on preprint servers. Some astronomers say the signals are meaningful. Others say they're calibration artifacts, the kind of thing that happens when you push instruments to their detection limits. The truth probably lies somewhere in the middle, but without access to the raw data and the full analysis pipeline, outsiders can't adjudicate these disputes. Let's think about what kinds of anomalies would actually point toward artificial origin. Non-thermal emission would be a big one. If 3I-ATLAS were emitting light or heat in ways that couldn't be explained by reflected sunlight, or thermal radiation from a warm surface, that would be deeply strange. Doppler shifts in spectral lines could indicate rotation or movement of components, but strange patterns like periodic modulation suggesting structure or machinery would be worth investigating. Any kind of radio emission would be extraordinary. Comets don't broadcast. They don't emit in organised frequencies. If we detected a signal, any signal, coming from 3I-ATLAS, the conversation would change instantly and completely. But we haven't detected anything like that. At least nothing has been publicly announced. The signals we have are ambiguous, statistical whispers that might mean something or might mean nothing. And that ambiguity is precisely where controversy lives, where some scientists see evidence worth pursuing and others see noise not worth the time. Which observatories or telescopes might hold key data that hasn't been released yet? JWST is the obvious candidate. It has the sensitivity to detect faint spectroscopic features that other instruments would miss. Ground-based arrays like the Very Large Telescope in Chile or the Keck Observatory in Hawaii could potentially contribute optical and infrared observations if they've been pointed in the right direction. The upcoming Vera Rubin Observatory, once it's fully operational, will have the capability to track thousands of faint objects, simultaneously, automatically flagging anything unusual. If 3I-ATLAS returns, or if similar objects appear, Rubin will catch them early. But for now, we're stuck with fragments. Pieces of data that don't assemble into a clear picture. Some pieces suggest a normal comet behaving normally. Other pieces hint at something weirder, something just off enough to make you pause. And without the full data set, without transparency from the agencies that control the best instruments, we can't resolve the contradictions. We're left guessing, filling gaps with speculation, wondering if the anomalies are real or if we're seeing patterns in randomness because we want to see patterns. In our next part, we're going to revisit the most provocative voice in this debate, Avi Loeb, the Harvard astronomer who's made a career out of taking anomalies seriously. We'll examine his arguments about 3I-ATLAS, how his ideas shape the narrative, and why his hypothesis attracts both fierce support and equally fierce skepticism. Because in science, personality matters. The messenger shapes how the message is received, and Loeb is a messenger who divides opinion like few others. Part 7. The Loeb Hypothesis Revisited. Avi Loeb is not a fringe figure. Let's establish that first. He's a professor at Harvard, former chair of the astronomy department, published hundreds of papers in peer-reviewed journals, recipient of numerous awards. He's mainstream by any conventional metric. But he's also become something else, a lightning rod. Because Loeb is willing to say things that other astronomers think but won't voice publicly, he's willing to entertain hypotheses that push against the boundaries of what's considered respectable scientific discourse. And that willingness has made him both a celebrity and a target. His fame began with Oumuamua, when that first interstellar object tumbled through our solar system in 2017. Most astronomers classified it as an asteroid or comet and moved on. Loeb looked at the data and saw something that bothered him. The object's trajectory showed slight accelerations that couldn't be easily explained by outgassing, because it didn't show signs of outgassing. Its brightness varied in ways suggesting an elongated shape, tumbling end over end. Its velocity and trajectory were consistent with what you'd expect from a deliberate object sent from another star, not a random rock kicked out of some distant planetary system. Loeb proposed, in a published paper, that Oumuamua might be a light sail, a thin reflective sheet propelled by starlight or laser, technology that humans have conceived of but not yet built. The hypothesis was scientifically rigorous, mathematically grounded, testable in principle. It was also incendiary. The response from the scientific community ranged from cautious interest to outright hostility. Some praised him for thinking outside the box. Others accused him of seeking attention, of lowering the standards of scientific discourse, of giving credibility to pseudoscience by entertaining exotic explanations when mundane ones were available. That background shapes how we should understand his stance on 3I-ATLAS. Loeb has been vocal about this object, arguing through published Q&As and public statements that we should take the anomalies seriously rather than dismissing them reflexively. His core claims go something like this. The brightness of 3I-ATLAS implies a large object or a highly reflective surface. The trajectory is, in his words, too neat, too precisely aligned with what you'd expect from something targeting the inner solar system, rather than tumbling chaotically. The lack of expected coma or tail, or the ambiguity about those features, doesn't match normal comet behaviour at this distance from the Sun. And he raises the possibility, not as certainty but as hypothesis, that manoeuvres could have occurred during occultation behind the Sun, when we couldn't observe the object directly, adjustments to course that we'd have no way of detecting after the fact. He also points to the minimal or absent non-gravitational forces. For a comet of 3I-ATLAS's size, approaching the Sun, you'd expect measurable outgassing effects on the trajectory. The object should be shedding material, creating thrust, showing up in orbital residuals as deviations from pure Keplerian motion. If those forces are smaller than expected or not detected at all, that's worth investigating. Either the object is composed of something unusually refractory, ices that don't sublimate easily, or it's not made of ice at all. The scientific community's response to Loeb's arguments about 3I-ATLAS has been predictably mixed. Many astronomers maintain that the observations still align with a comet, that the anomalies Loeb highlights can be explained by dust behaviour, calibration uncertainties, or simply the limitations of our data. One researcher was quoted saying something like, "Extraordinary claims require extraordinary evidence, and what we have is ordinary evidence of an ordinary object observed under difficult conditions." Another pointed out that interstellar space is different from the environment where our solar system's comets formed, so we should expect compositional differences, unusual ice mixtures, behaviours that don't match our local templates. The debate has an academic political dimension that's impossible to ignore. Exotic hypotheses attract attention. They get media coverage, book deals, speaking invitations. They also attract skepticism and professional risk. If you're wrong about something exotic, you damage your reputation far more than if you're wrong about something mundane. Peer review in top journals becomes harder when your hypothesis is controversial. Funding agencies are cautious about supporting research that might be seen as speculative or unserious. The incentive structure of modern science pushes toward conservatism, toward explanations that fit within established frameworks, toward not sticking your neck out too far. Loeb is aware of these dynamics. He's written about them extensively, arguing that science has become too conservative, too quick to dismiss anomalies, too attached to consensus thinking. He frames his approach as Galilean, as returning to a time when scientists were willing to challenge established beliefs based on observational evidence. His critics frame his approach differently, as attention-seeking, as lowering standards, as conflating possibility with plausibility in ways that mislead the public. But here's what Loeb gets right. Regardless of whether his specific hypotheses pan out, anomalies force us to refine our methods. Even if 3I-ATLAS turns out to be a perfectly normal comet with slightly unusual composition, the process of investigating it, of ruling out exotic explanations, of pushing our instruments and models to their limits, that process makes us better scientists. We learn more about what comets can be, how interstellar environments differ from our local neighbourhood, what signatures we should expect from truly anomalous objects if they ever appear. Loeb often invokes a lessons framing. He says we should use objects like 3I-ATLAS as teaching moments, as opportunities to think about what we'd look for if we were searching for extraterrestrial technology. What would the signatures be? How would we distinguish artificial from natural? What observations would conclusively rule in or rule out intelligence? These are valid scientific questions, worth pursuing even if the answer in this case is, it's just a comet, because the next object might not be. And if we haven't thought through the methodology, if we haven't prepared ourselves mentally and technically, we'll miss it, or dismiss it reflexively. The tension between Loeb and the broader scientific community reflects a deeper tension in how science should operate. Should we be conservative, demanding overwhelming evidence before considering exotic explanations? Or should we be exploratory, entertaining unusual hypotheses as long as they're testable, using them to drive observation and analysis even if they're unlikely? Both approaches have merit. Both have risks. Too much conservatism means we miss genuine discoveries because they don't fit our expectations. Too much openness means we waste time and resources chasing phantoms, diluting scientific credibility with speculation. 3I-ATLAS sits right in that tension. It's strange enough to warrant attention, normal enough to dismiss. Loeb and others like him push us toward the attention end of that spectrum. Critics pull us back toward dismissal. And somewhere in the middle is where the truth probably lives, waiting for better data to reveal itself. But that data has to be collected, those observations have to be made, and someone has to be willing to look, even if looking means being wrong. In our next part, we're going to shift perspective and look at who else might be watching 3I-ATLAS. Players beyond government space agencies, private observatories, commercial networks, entities that might have seen something but chosen to stay quiet for their own reasons. Because in the modern world, space observation is not a monopoly. The tools are distributed, the watchers are many, and information doesn't always flow through official channels. Part 8. Hidden Players. The romantic image of astronomy is a lone scientist at a telescope peering into the night sky, notebook in hand. That image is outdated. Modern astronomy is industrial, networked, automated. Telescopes scan the sky, continuously, feeding data into pipelines that process millions of observations per night. And not all of those telescopes are government-owned. Not all of that data flows through official channels. The democratization of space observation has created a parallel universe of watchers, and some of them might know things that haven't made it into press releases. Private observatories have proliferated in recent decades. Wealthy individuals, universities, research consortiums, they've built facilities with capabilities that rival government installations. The Las Cumbres Observatory operates a global network of robotic telescopes that can be tasked for custom observations. Planetary Resources, before it pivoted away from asteroid mining, developed techniques for tracking small bodies with commercial imaging systems. Amateur astronomers, equipped with CCD cameras and sophisticated software, regularly discover supernovae, asteroids, comets. The boundary between professional and amateur has blurred to the point where the distinction is more about funding than capability. Could any of these private entities have observed 3I-ATLAS in ways that revealed something unusual? It's plausible. A well-equipped amateur with a 16-inch telescope and a cooled CCD camera can detect objects fainter than what was visible to professionals 50 years ago. Networks like the International Astronomical Union's Minor Planet Center rely on amateur contributions for tracking data. If someone captured something anomalous, a structural feature, an unexpected emission, a deviation from predicted position, they might have reported it through official channels. Or they might have kept it to themselves, unsure of what they were seeing, unwilling to make claims without confirmation. There are rumours, whispers in online forums that get scrubbed or deleted. Someone claims they captured a streak image of 3I-ATLAS showing bifurcation, as if the object had split or had multiple components. The post gets challenged, arguments erupt about image artifacts versus real features, and then the original poster deletes everything. Another user claims their automated all-sky camera caught an anomalous brightening event, a sudden spike in luminosity that didn't match impact or outgassing models. That post also disappears. Are these real observations that got suppressed, either self-censored by nervous observers or removed by moderators trying to keep speculation under control? Or are they hoaxes, attention-seeking fabrications that got called out and deleted in shame? We can't know without access to the original data, and that's the problem. In the age of information, data can vanish as easily as it appears. Screenshots prove nothing. Eyewitness accounts carry no weight without corroboration. The signal-to-noise ratio in online astronomy communities is high, making it difficult to separate genuine anomaly reports from noise. Now, let's expand the scope. Spacefaring corporations have assets in orbit that aren't primarily scientific instruments, but could potentially observe deep space objects opportunistically. SpaceX operates thousands of Starlink satellites. Blue Origin is developing orbital infrastructure. Chinese private space firms are launching commercial payloads. These satellites have cameras, sensors, communication arrays. Most are pointed at Earth or at each other, but some have wide-field cameras for navigation, for monitoring orbital debris, for situational awareness. Could any of these systems have captured 3I-ATLAS? The geometry would have to align perfectly. The object would need to pass through a satellite's field of view at a time when the camera was active and the exposure settings were appropriate for detecting faint objects. It's a long shot, but not impossible. And if it happened, if a commercial satellite captured imagery of an interstellar object showing something unexpected, what would the company do? Release it publicly? Sell it? Keep it proprietary? Use it for internal research? There's no legal obligation for commercial entities to share astronomical data. They can do whatever they want with their observations. Then there's the possibility of secret radar or LIDAR experiments. Deep space radar is theoretically capable of detecting and profiling objects at significant distances, much farther than optical telescopes can resolve detail. The Arecibo telescope, before its collapse, could bounce radar signals off near-Earth asteroids and create detailed surface maps. Smaller systems exist, some operated by defense departments, some by research institutions, some by entities that don't advertise their capabilities. If 3I-ATLAS passed close enough to Earth, if someone pointed a powerful radar system at it, they might have gotten range Doppler imagery showing shape, rotation, surface features. Would such data be public? Probably not. Radar systems used for space surveillance are often dual use, meaning they also track satellites, debris, potentially adversarial spacecraft. The capabilities of these systems are classified. If they observed 3I-ATLAS, the data would likely be classified too, not because the object itself is secret, but because revealing the data would reveal the system's capabilities. This is standard operational security, not conspiracy. But from the outside, it creates another black box, another place where information might exist but remains hidden. Communication satellites also have a role to play. These satellites monitor vast swathes of radio spectrum looking for signals, interference, anything that might affect their operations. If 3I-ATLAS were emitting radio waves, even faintly, even intermittently, a communication satellite might detect it as anomalous background noise. Again, would that data be public? Communication companies are not in the business of astronomy. They'd have no reason to analyse or share such data unless it directly impacted their services. It might sit in logs somewhere, unexamined, unreported. Historical analogies help here. During the Cold War, early satellite imagery was classified for decades. The technology to photograph Earth from space was revolutionary, and governments didn't want adversaries knowing the resolution, the coverage, the capabilities. Dual-use data, information that has both scientific and military applications, gets treated cautiously. 3I-ATLAS is not a military target, but the systems used to observe it might be sensitive, and that sensitivity creates barriers to transparency. So we're left with a landscape where information might exist in corporate servers, in classified databases, in amateur hard drives, in logs and caches that no one has thought to examine or share. The official story, the one told through press releases and scientific papers, is always incomplete. It's the tip of the iceberg. Below the surface, there's a whole ecosystem of observation and data that never makes it into public discourse. Could some players already know more than the public knows? Could they be waiting to reveal or monetize it? The incentives vary. A corporation might wait for the right moment to announce a discovery, using it for marketing or to attract investment. A defense agency might never reveal anything, keeping the data locked away indefinitely. An amateur might be sitting on something significant, but lack the credibility or platform to get anyone to take it seriously. The ecosystem is fragmented, and fragmentation creates gaps where information hides. In our next part, we're going to explore why global powers might choose strategic silence instead of open disclosure. We'll move from the technical possibilities into the realm of strategy, politics, and the complex calculations that governments make when faced with information that could disrupt societies or reveal capabilities they'd rather keep hidden. Because silence is not always about uncertainty. Sometimes it's about control. Part 9. Cosmic Conspiracies. Let's ask the uncomfortable question directly. Why would governments or space agencies stay silent about 3I-ATLAS if they knew something significant? We've danced around this question for several parts now, but it's time to confront it head-on. Not because conspiracy is the most likely explanation, but because understanding the incentives for secrecy helps us interpret the patterns we're seeing. Governments don't operate on scientific principles alone. They operate on strategic calculations, risk assessments, political considerations that have nothing to do with truth and everything to do with control. First motive: controlling the narrative and public reaction. Governments are obsessed with managing how information flows to the public. This isn't inherently sinister. It's rooted in a belief, sometimes justified and sometimes not, that people will panic or react irrationally if given certain information without proper framing. If 3I-ATLAS showed features suggesting artificial origin, imagine the reaction. Stock markets would likely fluctuate based on uncertainty about what it means for humanity's future. Religious institutions would scramble to integrate this information into their worldviews. Political movements might form around competing interpretations, some demanding immediate disclosure of all information, others demanding that we prepare for potential threats. Managing that chaos is a powerful incentive to say nothing until you have a clear, controlled message. Second motive: avoiding mass speculation. Even without concrete evidence of anything anomalous, The mere suggestion that an interstellar object might be artificial would trigger speculation far beyond what evidence supports. We've seen this with UAP disclosures. The Pentagon released videos of aerial phenomena they couldn't explain, and immediately the public conversation jumped to aliens, despite officials carefully not making that claim. With 3I-ATLAS, if agencies suggested anything unusual, the speculation would explode, and walking it back later would be nearly impossible. Better to stay silent until certainty is high enough that speculation can be replaced with facts. Third motive, protecting sensitive defence or communication interests. Space-based observation systems are dual use. They watch asteroids, but they also watch satellites, debris, potentially adversarial spacecraft. If 3I-ATLAS were observed by classified systems, revealing what those systems saw would reveal their capabilities, their resolution, their sensitivity. Adversaries pay attention to what gets disclosed. They reverse engineer capabilities from published data. Protecting those capabilities might mean keeping observations classified, even when the object itself is scientifically interesting. Fourth motive, buying time to confirm or debunk evidence. Science takes time. Verification takes time. If initial observations suggested something anomalous, responsible agencies would want to check, double-check, triple-check before making public statements. They'd want multiple independent confirmations. They'd want to rule out artifacts, instrumental errors, misinterpretations. That process could take weeks or months. During that time, silence is the conservative choice, the safe choice, even if it frustrates the public and fuels speculation. Fifth motive, diplomatic and strategic positioning. If 3I-ATLAS is significant, if it represents something genuinely anomalous, different nations might want to position themselves advantageously before information becomes public. Maybe China wants to complete its own analysis before NASA announces findings, so they're not seen as reacting to American claims. Maybe the United States wants to coordinate with allies before going public, ensuring a unified message. These strategic calculations can delay disclosure, not because of conspiracy, but because of the complex dance of international relations. Now let's introduce the black budget possibility. Defense departments around the world operate programs that don't appear in public budgets, that have minimal oversight, that exist in legal grey zones. The United States Department of Defense has historically run programs tracking objects in space, both terrestrial and otherwise. The Advanced Aerospace Threat Identification Program, revealed in 2017, was one such program focused on aerial phenomena. Are there equivalent programs focused on deep space objects? Almost certainly. They might not be called that. They might be buried within larger surveillance or reconnaissance initiatives. But the capability exists. If such a program detected something significant about 3I-ATLAS, would we ever hear about it? That depends entirely on what they detected and what strategic value the information holds. If it's scientifically interesting but not strategically relevant, it might eventually be declassified and released. If it has strategic implications, national security ramifications, or if it reveals sensitive collection methods, it might remain classified indefinitely. We'd never know. The absence of information is not evidence of absence when classified programs are involved. Historical parallels illuminate these dynamics. The Galileo project, Avi Loeb's initiative to search for extraterrestrial technology using open scientific methods, exists partly in response to the tension between open science and classified tracking. Loeb has argued that too much space surveillance happens behind classified walls, limiting scientific inquiry. During the Cold War, reconnaissance satellites were so secret that their very existence was classified for years. Data they collected, even when scientifically valuable, stayed locked away. UFO and UAP programs throughout the 20th century operated with minimal oversight, releasing information sporadically, often only when pressured by leaks or Freedom of Information Act requests. The pattern is clear: when information intersects with national security, even tangentially, transparency suffers. And 3I-ATLAS, despite being a natural object or potentially natural object, intersects with space surveillance systems that absolutely have national security dimensions. That intersection creates barriers to openness. Let me walk through a hypothetical scenario. Imagine a classified detection occurred, an observation by a system that officially doesn't exist, or whose capabilities are not public knowledge. That observation shows something unexpected. maybe surface features inconsistent with a comet, maybe a faint emission in an unexpected wavelength, maybe trajectory adjustments that require explanation. What happens next? First, the data gets flagged and escalated. Someone decides it's significant enough to brief higher-ups. Second, verification begins. They task other systems, try to corroborate. With independent sensors, check for instrumental artifacts. Third, if verification holds, discussions begin about what to do with the information. Legal experts weigh in on classification requirements. Scientific advisors assess whether civilian astronomers might independently discover the same thing. Strategic planners consider geopolitical implications. Public affairs officers start drafting potential statements, planning how to manage disclosure if it becomes necessary. This process takes time, easily weeks or months. During this time, public-facing agencies like NASA might be informed, but they'd be constrained in what they can say. They can't reference classified observations. They can't hint at information sources they're not supposed to acknowledge, so they say nothing, or they issue bland reassurances based only on unclassified data. From the outside, this looks like concealment or incompetence. From the inside, it's standard procedure. Eventually, one of several outcomes occurs. Either the anomaly is explained away, classified as instrumental error or natural phenomenon, and the information stays buried because there's no reason to declassify it. Or the anomaly persists, gains weight, and a decision is made about managed disclosure. In that scenario, information gets released gradually, carefully framed, coordinated across agencies and possibly across nations. The public gets told a story that's true but incomplete, designed to inform without revealing sensitive capabilities. Is this happening with 3I-ATLAS? We have no evidence that it is, but we have no evidence that it isn't either. The infrastructure for exactly this kind of scenario exists. The precedents exist. The incentives exist. Whether those ingredients have combined in this case remains speculation, but it's informed speculation based on how governments actually operate, not paranoid fantasy. Counter-arguments matter here. Transparency pressure is real. In democracies, governments face oversight, leaks, whistleblowers, journalists who dig for buried stories. Scientific peer review creates its own transparency imperatives. If NASA scientists know something significant, many of them would want to publish, to share with the community, regardless of what officials prefer. Leaks happen. The Pentagon Papers leaked. Snowden leaked. Classified space programs have been revealed through leaks and investigative reporting. Perfect secrecy is nearly impossible to maintain long-term, so if there is something significant, if agencies are sitting on anomalous data, the silence probably can't last indefinitely. Eventually someone talks, someone leaks, someone publishes. The question is how long the silence can be maintained before it breaks, and what happens to the information in the meantime. In our next part, we're going to shift gears entirely. We're going to move from intrigue to theory, asking, if 3I-ATLAS is an alien artifact, what does silence itself tell us about its design, purpose, and constraints? We'll enter the realm of speculative physics, exploring what a probe's quietness might reveal about its makers and their intentions. Because sometimes the absence of signal is the signal. Part 10. Speculative Physics of Silence. Let's engage in a thought experiment. Assume, just for the next few minutes, that 3I-ATLAS is not a comet. Assume it's an artifact, a probe sent by intelligence from another star system. Now, ask, what does its silence tell us? Not the silence of governments, but the silence of the object itself. Why would an interstellar probe designed to explore or observe remain quiet, emitting no signals, making no attempts to contact us, appearing as nothing more than a faint fuzzy blob in our telescopes? The first answer is stealth. If you wanted to observe without being noticed, you'd minimize every detectable signature. No radio transmissions, because those would announce your presence across vast distances. No unnecessary thermal emissions, because heat is detectable in infrared. No bright surfaces or reflective panels, because they'd catch sunlight and draw attention. You'd design for minimal visibility, making yourself look as much like a natural object as possible. A stealth probe would have a dark, non-reflective hull. It might be covered in material that absorbs rather than reflects light. It might use passive cooling, radiating heat slowly in directions away from likely observers. This kind of design makes sense if your purpose is observation without interference. Maybe the probe's makers want to study civilizations without contaminating the study without introducing the variable of contact into the equation. We do this ourselves with wildlife observation. We use camera traps, remote sensors, techniques that let us watch animals without them knowing we're watching. A probe operating on the same principle would stay hidden, gathering data silently, reporting back through channels we can't detect. The second answer is energy conservation. Interstellar travel is expensive in energy terms. Accelerating even a small mass to a significant fraction of light speed requires enormous energy. A probe might not carry enough fuel or power generation capacity for active signaling, especially if it's intended to operate for centuries or millennia. Instead, it might rely on passive data collection, storing information, waiting for a rendezvous with another probe or a mothership, or simply recording for its own purposes without needing to transmit immediately. Passive power scavenging fits this model. The probe might harvest energy from starlight through ultra-efficient solar panels, or collect particles from the interstellar medium, or even use radioactive decay of onboard materials for a slow, steady trickle of power. All of these methods provide limited energy, enough for basic functions but not enough for high-power transmissions. The probe stays quiet, because it has no choice. It's operating on a budget, every watt accounted for, every function optimized for efficiency over communication. The third answer is AI-driven autonomy, with specific mission parameters. Imagine the probe is intelligent, equipped with artificial intelligence capable of making decisions, but constrained by programming that dictates its behavior. Its instructions might be simple: observe but don't contact. Collect data on planetary systems, on technological civilizations if encountered, but maintain distance. Report findings only under specific conditions, or never report at all if the mission is purely archival. An AI probe doesn't have curiosity or desire. It follows programming. If that programming says stay quiet, it stays quiet. This connects to concepts from CT and the Fermi paradox. The zoo hypothesis suggests that extraterrestrial civilizations might be deliberately avoiding contact with us, treating Earth as a nature preserve, watching but not interfering. A probe operating under zoo hypothesis parameters would be designed for observation without contact, explaining both its presence and its silence. The lurker hypothesis is related. Probes might be stationed throughout the galaxy, dormant, waiting for specific triggers before activating. Maybe the trigger is technological maturity, the point when a civilization develops certain capabilities. Maybe the trigger is a signal we're supposed to send. Until the trigger condition is met, the lurker remains silent. Cryptographic or quantum communication offers another explanation. If the probe is transmitting, but using methods we don't yet have the technology to detect, its communications would be invisible to us. Quantum entanglement could allow instantaneous communication without classical signals travelling through space. Highly directional, low-power laser links could send information in narrow beams that we'd never intercept unless we were directly in line with the target. Spread spectrum techniques could distribute a signal across such a wide frequency range that it looks like noise unless you know the decoding key. Human radio and television broadcasts leak into space, creating a detectable signature for any civilization with sensitive receivers, but that's inefficient. It's the equivalent of shouting when you could whisper. An advanced civilization would likely use communication methods that minimize leakage, that direct information precisely where it needs to go, without wasting energy broadcasting to the void. From our perspective, such communications would be indistinguishable from silence. The probe might be chatty, just not in a way we can hear. Energy constraints illuminate why silence might be the optimal strategy. Interstellar space is cold, close to absolute zero. Any active system generates waste heat, and disposing of that heat without radiating detectably is challenging. A probe might use radiators pointed away from likely observers, shedding heat into the cosmic microwave background. It might operate at very low power, processing data slowly, waiting long periods between active phases, minimizing heat, minimizing emissions, minimizing any signature that could be detected. All of this serves stealth and efficiency simultaneously. Could this explain why we only see a faint blob? Maybe the blob is deliberate, a minimal surface reflecting just enough light to look comet-like, while hiding the probe's actual structure beneath layers of dust or ice. Natural camouflage accumulated over the probe's journey through interstellar space. Or maybe the fuzziness is a cloud of particles the probe generates to obscure itself, a dust screen that makes detailed imaging impossible. We're looking at the camouflage, not the object. These ideas are speculative, but they're grounded in physics, not fantasy. We can build probes that minimize emissions. We know about stealth technology, about passive observation, about energy constraints. Extrapolating these principles to an interstellar context is reasonable, a way of thinking through what's possible given known physics. It doesn't prove 3I-ATLAS is artificial. It just maps out what artificial might look like so we know what to search for. The speculation serves a purpose. It sharpens our observational strategies. If we think a probe might use quantum communication, we develop quantum detectors. If we think it might radiate waste heat in specific directions, we position observers to catch those emissions. If we think it might be hiding under dust, we develop techniques for penetrating that dust with radar or other wavelengths. Even if 3I-ATLAS is just a comet, thinking through these scenarios prepares us for the real thing, if it ever arrives. Now we're going to shift away from 3I-ATLAS for a while. We're going to scan the wider frontier of 2025 science, looking at other anomalies, other silences, other places where the cosmos whispers, and we struggle to interpret the whispers. Because 3I-ATLAS is not happening in isolation. It's part of a larger pattern of mysteries, discoveries, and questions that define our current moment in scientific history. Understanding that context helps us see 3I-ATLAS more clearly, see how it fits into the bigger picture of our cosmic awakening. Part 11. Solar superstorms and hidden risks. The Sun tried to remind us who's boss in May and June of 2025. Coronal mass ejections, massive eruptions of plasma and magnetic fields from the Sun's surface slammed into Earth's magnetosphere with enough force to trigger global geomagnetic alerts. Auroras danced at latitudes far south of their usual range. Satellite operators scrambled to protect their assets. Power grid managers watched nervously, ready to implement emergency protocols if things got worse. For a few days, the threat was real. Not existential, but significant. The kind of event that could knock out communication satellites, disrupt GPS, damage transformers in power grids, plunge regions into darkness for weeks or months. A coronal mass ejection is not subtle. The Sun ejects billions of tons of charged particles into space at speeds approaching 1,000,000 miles per hour. When that cloud of plasma hits Earth's magnetic field, the field compresses, fluctuates, induces currents in anything conductive, including long power lines and pipelines. The Carrington event in 1859, the most powerful geomagnetic storm in recorded history, induced currents so strong that telegraph systems sparked and caught fire. If a similar event happened today, with our vastly more complex and vulnerable infrastructure, the damage could run into trillions of dollars, affecting billions of people. But here's why this matters for our story. Space threats exist on a spectrum, and agencies treat them conservatively. The Sun is predictable in some ways, wildly unpredictable in others. We can see CMEs leave the Sun and calculate when they'll hit Earth, but we can't always predict their intensity or their exact magnetic orientation, which determines how much damage they'll cause. Despite this uncertainty, space weather agencies issue alerts, warnings, forecasts. They communicate because the threat is understood, the physics is known, the response protocols are established. Contrast that with 3I-ATLAS, an object we don't fully understand, exhibiting behaviours that might or might not be anomalous, approaching through the inner solar system with no clear threat but plenty of ambiguity. How do agencies handle that? They treat it conservatively, which means they say very little until they know more. They don't want to alarm the public over something that might be nothing. They don't want to create panic or speculation without concrete evidence of danger or significance. So they default to silence, or to bland reassurances that communicate nothing of substance. This is a pattern. Known threats generate communication. Unknown or ambiguous threats generate silence. It's a risk management strategy. Talking about a coronal mass ejection is safe because everyone understands the threat is natural, temporary, manageable. Talking about an interstellar object that might be anomalous opens doors to questions agencies aren't prepared to answer. What if it's artificial? What if it changes course? What if there are more? Better to say nothing than to trigger those questions prematurely. New solar weather forecasting research in 2025 is helping predict severity and mitigation more accurately. Machine learning models trained on decades of solar observation data can now forecast CME intensity with improved confidence. Satellite constellations monitor the Sun continuously from multiple angles, providing stereoscopic views that help predict how ejected material will evolve as it travels toward Earth. These advances give us more warning time, more accurate predictions, better ability to protect infrastructure, and this information gets shared openly, published in journals, discussed at conferences, integrated into public forecasting systems. Why the difference? Because solar weather is a known quantity, a threat we've domesticated through understanding. 3I-ATLAS represents the unknown, the undomesticated, the category of things we haven't learned to manage yet, and humans, including scientists and bureaucrats, handle the unknown differently than the known. The unknown gets quarantined, kept at arm's length, studied cautiously before being integrated into public discourse. The cosmos is noisy. Signals bombard us constantly. Radio waves from distant galaxies, neutrinos from supernova, gravitational waves from colliding black holes, the hiss of the cosmic microwave background radiation. Most of this noise we ignore because it's expected, because it fits our models. But when something doesn't fit, when a signal arrives that challenges our frameworks, the noise becomes deafening in a different way. The noise of speculation, of competing interpretations, of uncertainty that resists resolution. And sometimes the response to that noise is to mute the conversation until clarity emerges. 3I-ATLAS is one note in that cosmic symphony. Solar storms are another. In our next part, we're going to dive into dark matter whispers, another cosmic anomaly that lives in the territory between detection and confirmation, where physics pushes against the boundaries of what we can observe and understand. Because the universe is full of things we can't see directly, can only infer from their effects, and dark matter is the biggest invisible presence of all. Part 12. Dark Matter Signal Tease. Deep underground, shielded from cosmic rays by miles of rock, detectors wait in the dark. These instruments, cooled to temperatures near absolute zero, sit watching for something that might not come. They're hunting dark matter, the invisible substance that makes up 85% of the matter in the universe, but has never been directly detected. We know dark matter exists because we can see its gravitational effects. Galaxies rotate too fast for the visible matter they contain. Galaxy clusters hold together despite not having enough mass in stars and gas. Gravitational lensing bends light in ways that require more mass than we can see. Something is out there. Something with mass. Something that doesn't emit or absorb light. We call it dark matter, but that's just a placeholder for our ignorance. In 2025, whispers have emerged from the underground facilities. Not confirmed detections, not publishable results, but anomalies, clusters of events that don't quite fit background expectations. One detector in Italy, the Easton collaboration, or one of its successor experiments, reported an excess of events in a specific energy range. The excess was small, barely statistically significant, the kind of thing that could be explained by contamination, calibration drift, or random fluctuation. But it was there, persistent across multiple data runs, enough to make physicists pay attention without getting excited. Dark matter particles, if they exist, would pass through ordinary matter almost without interaction. Only occasionally, maybe once every few months in a ton of detector material, would a dark matter particle collide with an atomic nucleus, producing a tiny flash of light or a minute energy deposit. That's what these underground detectors are built to catch, those incredibly rare collisions, signals so faint they barely rise above the noise. Distinguishing a real dark matter signal from background noise requires years of data, exquisite calibration, multiple independent confirmations. The whispers from 2025 don't constitute confirmation. They're more like tantalizing hints, possibilities that need more time, more data, more scrutiny before anyone will claim discovery. But they're not nothing. They're the kind of anomaly that drives physicists to check their instruments, reanalyze their data, consider whether they're seeing the first faint signature of something real. To explain this to a general audience, imagine trying to hear a whisper in a crowded stadium. That whisper is dark matter. The crowd noise is background radiation, cosmic rays, radioactive decay from the detector materials themselves, every other source of energy that creates signals. To hear the whisper, you need to eliminate as much of the crowd noise as possible. You go deep underground to block cosmic rays. You use ultra-pure materials to minimize radioactive contamination. You cool everything down to reduce thermal noise. You run the detector for years, accumulating data, waiting for the statistics to improve enough that a real signal, if it exists, will emerge from the noise. Now connect this to 3I-ATLAS. Both are stories about signals hiding in noise, about anomalies that might be something or might be nothing, about the difficulty of distinguishing real from artifact when you're operating at the limits of detection. Dark matter experiments are designed with this challenge in mind. They build in redundancy, multiple confirmation methods, strict statistical thresholds before claiming discovery. The process is slow, deliberate, conservative. Astronomy doesn't always have that luxury. 3I-ATLAS passed through the inner solar system on a schedule we didn't control. We got one chance, maybe a few weeks of optimal observation, and then it was gone. The data we collected is all we'll have unless it comes back, which seems unlikely given its hyperbolic trajectory. So the evidentiary standard is different. We can't wait years for confirmation. We have to work with what we got, interpret it as best we can, acknowledge uncertainty but still draw conclusions. This creates asymmetry in how discoveries get announced. Dark matter experiments can afford to wait to say, we saw something interesting, but we're not calling it a detection yet. Astronomers observing a transient object don't have that luxury, but they also face intense pressure not to overclaim, not to announce something dramatic that later falls apart. The result is a middle ground where they say very little, waiting for consensus that might never arrive because the object is already gone. The similarity is striking. We live in a universe full of signals, many hidden, many ambiguous, many buried in noise where extraction requires sophisticated techniques and patient analysis. 3I-ATLAS might be a loud exception. An interstellar visitor that should be obvious should generate clear, unambiguous data. But what if it's not? What if it's just another whisper in the stadium, and we're straining to hear it over all the other noise? There's a philosophical question lurking here. How many anomalies do we walk past because they don't fit the canonical story? Dark matter itself was an anomaly for decades before it became accepted. Fritz Zwicky proposed it in the 1930s based on observations of galaxy clusters. He called the missing mass dunkle Materie, dark matter. The scientific community largely ignored him. It wasn't until the 1970s, when Vera Rubin's rotation curve measurements made the case undeniable, that dark matter became mainstream. Decades of anomalies dismissed or explained away until the weight of evidence became too great to ignore. Could 3I-ATLAS be following a similar trajectory? An anomaly that's currently being dismissed or minimized, but that future observations or reanalysis will reveal as significant? Or is it the opposite, an anomaly that looks interesting now, but will be explained away as our understanding improves? We won't know for years, maybe decades. The dark matter story teaches us that patience is sometimes required, that not every anomaly resolves quickly, that some mysteries take generations to solve. But the dark matter story also teaches us about the sociology of science, about how anomalies that challenge existing frameworks get treated with skepticism until they can't be ignored anymore. Zwicky was right, but he was dismissed as eccentric, his ideas not taken seriously during his lifetime. Rubin faced gender-based discrimination on top of scientific skepticism. The path from anomaly to accepted fact is not smooth. It's jagged, political, influenced by factors that have nothing to do with the data itself. 3I-ATLAS exists in that sociology. Claims about its anomalous nature get filtered through the same dynamics that filtered dark matter claims. Who's making the claim? What's their reputation? How does the claim fit with existing theories? What are the political and professional risks of taking it seriously? These questions shape how anomalies get received, independent of their actual validity. In our next part, we're going to bring in a new player, artificial intelligence. AI is transforming how we process astronomical data, how we flag anomalies, how we decide what's worth human attention and what can be ignored. This transformation has profound implications for stories like 3I-ATLAS, because increasingly, AI systems are the first eyes on new data, the first filters deciding what gets elevated and what gets dismissed. And that introduces a whole new layer of complexity to the question of silence and signals. Part 13, AI's role in the cosmic watch. The universe generates more data than humans can process. Every night, telescopes around the world capture millions of images. Every second, radio telescopes record gigabytes of signal. Spectroscopes produce thousands of spectra. The volume is overwhelming, far beyond what human astronomers can examine individually. So we've built gatekeepers, artificial intelligence systems that process this flood, flag what's interesting, filter out what's not. These systems have become essential infrastructure, the first line of analysis between raw data and human eyes. China's 500-metre aperture spherical telescope, FAST, the world's largest single-dish radio telescope, has been upgraded with AI processing pipelines specifically designed to hunt for anomalies. The system analyses incoming radio signals in real time, comparing them against templates of known sources, flagging anything that doesn't match. It's looking for transients, for bursts, for patterns that might indicate technological signals. Similar systems are being deployed at other facilities. The upcoming Vera Rubin Observatory will use machine learning to process its massive survey data, automatically identifying supernovae, asteroids, variable stars, anything that changes or appears unexpectedly. NASA has integrated AI into multiple data pipelines. The James Webb Space Telescope uses machine learning for scheduling optimization, determining which targets to observe when, balancing scientific priorities against operational constraints. Ground-based surveys use neural networks trained to distinguish asteroids from stars, real objects from artifacts, interesting transients from boring background fluctuations. The AI doesn't make final decisions, but it narrows the field, directs human attention to the small fraction of data worth detailed examination. This is efficient, necessary even. Without these filters, we drown in data, miss important discoveries because they got lost in the noise. But it introduces a new kind of fragility. What if the AI filters out something important? What if its training data didn't include examples of whatever new phenomenon is occurring, so it misclassifies it as uninteresting? What if a truly anomalous signal, the kind we should care most about, gets flagged as error and automatically discarded? Machine learning systems learn from examples. You show them thousands of images of asteroids, teach them what asteroids look like, and they learn to recognize asteroids. But they also learn what not asteroids look like, and they'll tend to classify anything that doesn't fit their training distribution as noise or artifact. If 3I-ATLAS showed features unlike any comet in the training set, an AI system might flag it as suspicious, or it might dismiss it as corrupted data. The outcome depends on exactly how the system was trained, what its confidence thresholds are, how it handles edge cases. Here's a speculative scenario. Imagine an AI system processing images from Mars orbiters early in 3I-ATLAS's approach. The system sees a faint object, tries to classify it, finds it doesn't match any known category very well. It assigns low confidence, flags it as potential artifact, routes it to a low priority queue. By the time a human looks at it, weeks have passed, the observation window is closed, the object has moved on. The AI didn't intentionally suppress anything. It just followed its programming, its learned biases about what's real versus what's noise. But the effect is the same as deliberate suppression. Information that should have been elevated got buried. Or consider the opposite scenario. An AI flags 3I-ATLAS as highly anomalous, assigns it high priority, routes it immediately to human analysts. The humans look at it, see the same ambiguous data we've been discussing, decide the AI overreacted. They downgrade the priority, file it away, move on to things they consider more important. Here the AI did its job correctly, but the human filter killed the signal. The system failed not because of AI limitation, but because of human judgment applied too conservatively. These scenarios highlight a tension. Do we trust AI pipelines more than human-led observations? Each has failure modes. Humans have biases, limited attention, tendency to see what they expect to see. AI has training limitations, inability to generalize beyond its examples, no common sense to fall back on when facing truly novel situations. Ideally, we'd use both in complementary ways, AI for breadth and speed, humans for depth and judgment. But that requires good communication between the systems, and that communication isn't always perfect. There's another dimension, AI as gatekeeper, in the sense of deciding what becomes public. If an AI system flags something as highly anomalous, but the anomaly is ambiguous or potentially sensational, whoever controls that AI system faces a choice. Do they immediately release the finding, triggering public interest and scrutiny? Or do they investigate privately first, verify before announcing, control the narrative? The AI has done its job by flagging the anomaly. but humans decide what to do with that flag. In the future, this dynamic will intensify. As AI systems become more sophisticated, as they handle more of the data pipeline autonomously, the human role will shift from direct observation to oversight to monitoring the AI monitors. When that happens, silence might not be human anymore. It might be algorithmic, a consequence of how systems are designed and trained, rather than conscious choices by scientists or administrators. And that introduces new accountability questions. If an AI system misses or suppresses something important, who's responsible? The programmers who designed it, the institutions that deployed it, the training data that shaped its behavior. 3I-ATLAS was observed during a transition period. Some data processing was automated, some was manual. Some facilities had sophisticated AI pipelines, others relied on traditional methods. This heterogeneity creates gaps, places where information might slip through or get lost in translation between systems. It's not anyone's fault necessarily, it's just the messy reality of infrastructure in transition, old methods coexisting with new, neither perfect, both introducing different kinds of errors. In our next part, we're going to shift from the systems that detect signals to the nature of the signals themselves. Specifically, we're going to explore quantum communication, a leap in technology that might explain why certain signals are invisible to us. Because maybe the silence isn't about what's being said, but about how it's being said. In languages and through channels we don't yet have the vocabulary to hear. Maybe 3I-ATLAS is screaming, and we're just not listening at the right frequencies. Part 14. Quantum Communications Leap. 2025 saw breakthroughs in quantum communication that most people barely noticed. Satellite-based entangled photon experiments achieved new distance records, demonstrating that quantum encryption keys could be shared between continents with near-perfect security. Ground stations in China and Europe established quantum links that conventional eavesdropping couldn't penetrate. The technology moved from laboratory demonstration to practical deployment, a quiet revolution in how information can be transmitted. For those unfamiliar, quantum communication exploits the properties of entangled particles. When two photons are entangled, measuring the state of one instantly affects the state of the other, regardless of distance. This isn't faster-than-light communication in the sense that violates relativity. You still need a classical channel to complete the protocol, but it enables communication that's fundamentally secure and, from an outside observer's perspective, nearly undetectable. You can't intercept an entangled photon stream without disturbing it, and that disturbance is immediately obvious to the legitimate parties. Now apply this concept to interstellar communication. Imagine a civilization far more advanced than ours, one that's mastered quantum entanglement on cosmic scales. They could establish communication channels between probes and homeworlds that would be invisible to anyone not part of the entangled network. From our perspective, looking with radio telescopes or optical telescopes, we'd see nothing. No signals, no transmissions, no evidence of communication. The probe and its controllers could be in constant contact, exchanging vast amounts of information, and we'd be completely blind to it. This is not science fiction. The physics is understood, even if the engineering for interstellar distances is beyond us. If a probe like 3I-ATLAS were using quantum communication, we wouldn't detect it unless we happened to intercept and measure one of the entangled photons, and even then, we wouldn't be able to decode the information without knowing the encryption scheme. The channel would be silent from our perspective, not because nothing's being said, but because we're looking with the wrong kind of eyes. Highly directional, low-power laser links offer another invisibility mechanism. Instead of broadcasting radio signals in all directions, which is what our early technology did because it was simple, an advanced civilization would use tight beam lasers to send information directly to its target. The beam would be narrow, maybe microradians or even nanoradians, illuminating only a tiny patch of space. Unless you happen to be in that patch, unless the beam swept across Earth during your observation window, you'd never detect it. The energy efficiency of such systems is compelling. Broadcasting radio waves spherically means most of your signal dissipates into empty space, wasted. Pointing a laser beam means nearly all your energy goes where you want it, dramatically reducing power requirements. For a probe operating on limited energy, this efficiency might be necessary rather than optional. So the probe communicates constantly, but only in directions we can't observe, beams that miss us entirely or are so faint when they reach us that they're lost in background noise. Spread spectrum techniques. borrowed from military communications, offer yet another way to hide signals. You take your message and distribute it across an extremely wide frequency range, so thinly that at any given frequency it looks like noise. To decode the signal, you need to know the spreading pattern, the key that tells you how to reassemble the distributed pieces. Without that key, sophisticated receivers would see only random fluctuations, indistinguishable from thermal noise or cosmic background radiation. SETI, the search for extraterrestrial intelligence, has traditionally looked for narrowband signals, the kind that clearly indicate technological origin because they're too narrow to be produced by natural processes. But if alien communications use spread spectrum, we'd miss them completely. They'd be there, all around us potentially, but appearing as noise because we don't know the decoding pattern. It's like trying to understand a language you've never heard. It sounds like meaningless sounds until you learn the grammar and vocabulary. Human radio and television broadcasts leak into space inefficiently, a byproduct of our technology's immaturity. We're getting better, moving to fiber optics and directional transmitters, reducing our electromagnetic footprint. An advanced civilization would have made this transition long ago. They wouldn't leak. They'd communicate precisely, efficiently, invisibly to outsiders. From their perspective, broadcasting broadly would be like shouting your secrets in a crowded room, inefficient and potentially dangerous if there are hostile listeners. So when we search for signals from 3I-ATLAS, we search using our methods, our assumptions about how communication works. We look for radio transmissions, optical flashes, anything we know how to detect. But if the object is communicating using methods beyond our current technology, we could be standing in a conversation and never know it. This silence we perceive is not absence of communication. It's our own technical and conceptual limitations reflected back at us. This has profound implications for how we interpret the silence around 3I-ATLAS. Agencies might not be withholding information. They might simply have nothing to report because they're looking with the wrong tools. The object might be broadcasting constantly, a beacon visible to anyone with the right receivers, but we don't have those receivers yet. We're like someone from the 19th century trying to watch television. The signals are there, filling the air, but without the right technology to decode them, you'd never know. There's a humbling lesson here about the limits of knowledge. We tend to assume that if something exists, we detect it given sufficient effort. But that assumption only holds if the thing cooperates with our detection methods, if it exists in a form we're prepared to recognize. Quantum communication, directional lasers, spread spectrum encoding. These aren't exotic or impossible. They're extensions of technologies we already have, refined and optimized by civilizations with more time and resources. And they render traditional SETI approaches potentially obsolete, searching for signals that advanced civilizations no longer produce. The flip side is that this makes the search harder, maybe impossibly hard. If we can't detect signals because they're using technologies we don't have, how do we ever find them? The answer might be that we don't, not until we develop those technologies ourselves, or until they choose to make themselves visible using methods we can detect, deliberately dumbing down their communications for the benefit of less advanced observers. Whether 3I-ATLAS represents such a choice, a deliberate visibility, remains an open question. In our final part, we're going to turn the lens around entirely. We're going to examine our own silence, the decisions we make about what to disclose, what to withhold, what to emphasize or downplay. Because ultimately, the silence around 3I-ATLAS might be less about the object and more about us, our fears, our institutional structures, our choices about how to handle the unknown. And understanding that human dimension is essential to understanding the entire story. Part 15. The meta takeaway, our own silence. We've circled this question for 15 parts now, looking at it from every angle. The object, the observations, the agencies, the technologies, the possibilities. But maybe the most important question is not about 3I-ATLAS at all. Maybe it's about us. Why are we silent? Not the specific agencies or individuals, but we as a civilization, we as a species trying to understand our place in a cosmos that's far stranger and more complex than our ancestors imagined. The silence around 3I-ATLAS may ultimately be ours, not the object's. The object is what it is, whether comet or probe or something in between. It doesn't choose how to reveal itself beyond whatever physics or engineering determines its observable properties. But we choose how to observe, how to interpret, how to communicate what we find. and those choices are shaped by factors that have nothing to do with the object itself: institutional pressures, funding concerns, career considerations, fear of ridicule, fear of panic, strategic calculations that prioritize control over transparency. Let's address the ethical questions first. What should scientists publish versus withhold? The traditional answer is everything, subject only to peer review and verification. Science advances through openness, through sharing data and methods so others can replicate, challenge, extend. But that ideal butts up against practical realities. Some discoveries have national security implications. Some findings, if released prematurely, could cause public harm through misinterpretation or panic. Some data is proprietary, collected using instruments or methods that competitive advantage depends on keeping secret. The tension between openness and these countervailing pressures is not easily resolved. Who gets to decide when an anomaly is safe to reveal? In democratic societies, theoretically the public decides through elected representatives who oversee scientific institutions. In practice, decisions get made by unelected administrators, scientists with institutional affiliations, funding agencies that set priorities. The public learns what filters through these layers, what survives the review processes, what gets deemed suitable for general consumption. This isn't necessarily sinister. It's how complex societies function. But it creates distance between discovery and disclosure, and in that distance, information can be shaped, delayed, or lost. How do national security concerns, public panic risks, and funding pressures shape disclosure? Enormously. A space agency considering whether to announce an anomalous finding has to game out the consequences. Will Congress respond by increasing their budget to study the anomaly, or by cutting funding because the agency looks unreliable? Will the public engage constructively, or will conspiracy theories and panic dominate the reaction? Will international partners share more data, or will they close ranks and withhold? These questions have real answers that affect real careers and institutions, and they influence behaviour in ways that slow or stop disclosure, even when no formal suppression is intended. Bring in analogous controversies from 2025. In genetics, debates raged about when and how to release findings about hereditary disease risks. Release too early, before therapies are available, and you create anxiety without offering solutions. Release too late, and people who could have benefited from early screening miss opportunities. In artificial intelligence, researchers debated whether to publish certain algorithmic advances that could be weaponized or used for surveillance. In climate science, questions persisted about how to communicate projections without either understating risks or paralysing the public with doom. These are not simple questions with obvious answers. They're judgment calls that reasonable people disagree about, and 3I-ATLAS falls into the same category. If observations suggest something genuinely anomalous, something that might indicate intelligence, when and how should that be announced? After all verification is complete, after international consultation, immediately to allow global participation in further observation? There are arguments for each approach, and choosing wrong can have consequences. Emphasise that delays are often structural, not intentional. Large institutions move slowly. Data has to be processed, analysed, reviewed by multiple parties before it's ready for publication. This takes time, especially for complex or unusual findings that don't fit standard templates. What looks like suppression from outside might just be the normal pace of institutional work, slowed further by the extraordinary nature of the finding. Bureaucracies are not designed for speed. They're designed for thoroughness, for minimising errors, for covering institutional liability. Those design goals conflict with rapid disclosure. Circle back to 3I-ATLAS. If we assume silence is evidence, we need to be wary of self-fulfilling prophecy. The longer agencies stay quiet, the more suspicious their silence appears, the more people assume something is being hidden. That assumption then colours how any eventual disclosure is received. If agencies finally release more data showing 3I-ATLAS is just a comet, skeptics will claim cover-up, selective disclosure, hiding the good stuff. If they release data showing anomalies, critics will ask why it took so long. The silence creates a no-win situation where institutional credibility suffers, regardless of what the truth turns out to be. This is the paradox of conspiracy thinking. It's unfalsifiable. Evidence against conspiracy gets interpreted as part of the conspiracy. Lack of evidence gets interpreted as successful suppression, The only way to break this loop is radical transparency, releasing everything immediately, but that has its own costs and is often impossible given legitimate privacy, security, or verification concerns. So institutions are trapped, unable to satisfy skeptics without compromising other values they're supposed to uphold. Offer a balanced takeaway. Moving forward, vigilance dictates that every silence be questioned, but responsibly. Question why agencies delay, why data isn't shared, why certain findings get emphasized while others are minimized. But also recognize that not every delay is nefarious. Not every silence is suppression. Sometimes silence is caution. Sometimes it's uncertainty. Sometimes it's just the slow grinding of institutional gears. Distinguishing between these requires looking at patterns over time, at track records, at whether agencies eventually disclose or whether information only emerges through leaks and pressure. For 3I-ATLAS specifically, the responsible stance is to remain alert, monitor what agencies release, push for open data policies that make raw observations available to independent researchers, support initiatives like the Galileo project that aim to create parallel, transparent observation networks, demand accountability when delays seem excessive or explanations seem inadequate, but also extend some benefit of doubt, recognizing that ambiguous data genuinely creates difficult choices about what to say and when. The broader principle applies beyond this one object. We're entering an era where our instruments are sensitive enough to detect things we don't immediately understand. Fast radio bursts appeared from nowhere in the data, challenging our theories. Gravitational waves opened a new window on cosmic events we'd only imagined. The more we observe, the more anomalies we'll find, and each one will create these same tensions between disclosure and caution, between speculation and verification. Our choices about how to handle these tensions will define what kind of scientific civilization we become. Do we embrace transparency, accepting the messiness and uncertainty that comes with it? Or do we prioritize control, accepting the suspicion and delayed progress that creates? There's no perfect answer. Every approach has trade-offs. But being conscious of those trade-offs, making them explicit, debating them openly, that's essential. In the quiet between the stars, the loudest truth might already be waiting for us to listen. But listening requires more than instruments. It requires courage. The courage to hear things that challenge our frameworks. The courage to sit with uncertainty rather than rushing to premature conclusions. The courage to say, I don't know, when we don't know instead of inventing reassuring stories. And it requires trust. Trust that others are also trying to understand. Trust that institutions, however imperfect, are acting in good faith most of the time. Trust that truth will eventually emerge if we keep questioning, keep observing, keep demanding accountability. 3I-ATLAS will recede into the distance, eventually too faint for even our best instruments to track. But the questions it raised will remain. What are we willing to see? What are we prepared to acknowledge? How do we balance caution with curiosity, responsibility with transparency? These questions don't have final answers. They're questions we'll keep asking with every new discovery, every new anomaly, every new visitor from beyond our solar system. So monitor agency releases, stay curious, demand open data, support transparent science, but also practice epistemic humility, recognizing the limits of what we know and what we can know given current technology and methods. The universe is under no obligation to make itself easy to understand. It's vast, old, strange, operating on scales and principles that humble our pretensions to mastery. 3I-ATLAS is one tiny thread in that cosmic tapestry, and whether it's natural or artificial, whether it's ordinary or extraordinary, it reminds us that we're still at the beginning of our journey to understand this incredible universe we inhabit. The silence will break eventually. It always does. Data will accumulate, interpretations will sharpen, new observations will constrain possibilities. Maybe we'll confirm it's a comet, unusual but natural, and move on to the next mystery. Maybe we'll find evidence that genuinely challenges our understanding, that forces us to expand our conception of what's possible. Either way, the process continues. We observe, we question, we debate, we slowly build toward understanding. That's the scientific project, messy and slow and imperfect, but still the best method we have for navigating the unknown. And in that navigation, silence is not the enemy. Imposed silence, deliberate suppression, that's the enemy. but the silence of caution, of verification, of taking time to understand before speaking that silence has its place. The art is knowing the difference and demanding accountability when the wrong kind of silence prevails. With 3I-ATLAS, that art is still being practiced. We're still in the middle of the story, not at its end. And how the story concludes depends not just on what the object is, but on what we choose to do with the information we gather. So we wait and watch and question. We hold our agencies accountable while recognizing their constraints. We push for transparency while understanding the complexities that sometimes require caution. We remain open to extraordinary possibilities while demanding extraordinary evidence. And through all of this, we remember that the greatest silence we must overcome is not out there among the stars. It's within ourselves, the silence of assumptions unquestioned, of curiosity suppressed, of wonder lost to, cynicism or complacency. The universe is speaking. Whether through 3I-ATLAS or 1,000 other signals, it's telling us we're not alone in space and time. We're part of something far grander and stranger than we yet comprehend. Our task is to listen, truly listen, with all the tools and wisdom we can muster, and to keep listening even when the silence feels overwhelming, even when answers seem impossibly distant. Because in that persistence, in that refusal to stop questioning, lies our best hope of finally hearing what the cosmos has been trying to tell us all along.